What you're going to find in this next section here is things are very, very similar to what we've done in the past. Most of the problems that you do in this section will involve the use of Normalcdf and inverse norm in the same way, but the mean and standard deviation of a sampling distribution is different. So what I first need to do is to show you the different distributions that we have, and then go into this this lecture here after you understand a little bit about what a sampling distribution is. So I'm going to take an example from something that you're familiar with, and that might be just kind of rolling a die. Now, we know a lot about the probability distribution of rolling a die. If we just wrote the table, we would know that there would be, 6 different possible rolls, and the probability of each one would be 1/6. And if we drew the graph of this probability distribution here, where the horizontal scale is the probability, and the vertical scale is the probability, and the horizontal scale would be all of our outcomes, our x's, then we would have, 1, 2, 3, 4, 5, and 6. And the probability up here would be 1/6, and all the probabilities would be the same. We talked about a uniform distribution, but this is what it would look like. So clearly this is not bell-shaped. This is a uniform distribution. This is we would call a probability model. Theoretically, this is what it's supposed to look like. Now we can calculate here because we've done it. We've calculated the mean and the standard deviation of this distribution. And let me just go ahead and, this is not binomial, so I can't use a binomial distribution, but it is like a problem from 6.1, where we entered in all of the probabilities, all the different possible rolls of the die, and then all the probabilities associated with those. And when you type in 1 divided by 6 for each one of these, you get the decimal version. All right, so there is the same distribution as you see here. And then to calculate the mean and the standard deviation of this probability model, here's what we would need to do. Stat, calculate. Hopefully you've done this 30 or 40 times in your homework. L1, L2, and there it is. So the X bar, that's just the notation it gives, but that would be the mean. And what this means is that if you rolled this die billions and billions and billions of times and recorded all of the outcomes, the 1s, all the 2s, all the 3s, and all the 4s, you'd get about the same number of 1s, 2s, 3s, 4s, 5s, and 6s. And then if you averaged all those numbers, you'd get 3.5. The standard deviation is 1.708, something like that. So here's one distribution that we worked with. All right, now the second one is a single sample distribution. Now a sample requires, a number of trials. And so let's just go ahead and choose a large number of, let's just say that we're going to roll this die 600 times. And I'm just going to make these numbers up because this is a single sample. And if, if 10 different people roll the die 600 times and record the number of outcomes, this time I'm not going to write the the probability. I could probably do that later, but I'm going to start with writing the frequency. So let's say that of those total of 600 rolls, this is one particular sample. Would be very, very unusual to hit 100, 100, 100, 100, 100. But so maybe we did say 120 and 110 and 100. I'm just going to use some nice round numbers here. and maybe 100 down here, and then say 90 and 80. Maybe that's what it looks like. So then I could calculate the probability in this setting, but the probability would correspond to a relative frequency. So I just take the 120 and divide by 600, and the 110 divided by 600, and so on. I mean, we could write the decimals over there. All right, but again, what I'm interested in here is the mean and the standard deviation. And notice how I wrote the mean and the standard deviation here. This is not a theoretical model. This is based on a single sample. And since it's based on a single sample, I'm going to use our sample notation, our sample mean and sample standard deviation. And then if I wanted to calculate the mean and the standard deviation of just this, this one sample, then I still have the same 6 outcomes, but now I'm just going to put in the frequencies, 120, 110, 100, and so on. Just like you see here. Now I could calculate the probabilities if I want, but we don't have to do that here because these are frequencies here, and we know how to calculate the frequency, the mean of frequency data like this. This is our outcome list, possible roles, and these are the frequencies. So we can just go ahead and do one variable statistics again, L1 and L2. And now you'll see that there is a sample standard deviation because we're not putting in probabilities for that second list. We put in actual frequencies. So the mean was 3.33. And the standard deviation, that would be the SX, 1.749. And so I ask you to consider the differences between these two. Notice that the means are about the same. We would expect theoretically that the population mean to be 3.5 on average, but when we actually did sample, it ended up a little bit less than that. If someone else rolled the die 600 times and they calculated the mean and standard deviation, they would be slightly different. Every sample is going to be different. But what you'll find is that all of the samples, the means will be about the same and the standard deviations will be about the same. All right, so we've studied these first two, a probability distribution of rolling a die, and then if we took a single sample and rolled the die. Okay, now I want to give you the distribution that we're going to be looking at today. It's called the sampling distribution. And it's the sampling distribution of the sample mean. So this is a theoretical population model like the first one. And it turns out, and I'll explain this in a little bit more detail later on, but it turns out that, I mean, what this is, let's see, I'll just kind of draw a couple pictures for you. Here's the population of all the possible, just imagine, 7 million people rolling the die 600 times. And every time someone rolled the die 600 times, they calculated the mean. And then they gave me the mean, and I plotted the means. So I'm calculating, this is just one sample, but I'm going to pick out the sample mean from that sample. Then I'm going to do it again. Then I'm going to do it again. And I'm going to take all these samples from the population and record the mean over and over again. So we're going to get X1 bar and X2 bar and X3 bar and so on. We're calculating a bunch of means, and what we're interested in is drawing the graph of all those means. Well, it turns out that if we graphed all those means on a kind of like in a histogram like this, you would find that all of those means would kind of hover around, and if we just stacked them and oops, X bar 4, X bar 5, and so on, there's going to be a lot of variation in these means. But the more of them that you calculate over and over again, you're going to see a pattern emerge. And it turns out that the pattern is going to look bell-shaped if you took all the possible means and put them in here. The graph of the sampling distribution is going to look approximately bell-shaped. In fact, it's going to be approximately normal under certain circumstances. And what I've done up here is I've identified the mean and the standard deviation in each case. All right, so now you're going to have some new variables here. What we're going to be interested in, and this is actually the sampling distribution that we use later on in chapters 9 and 10. It's called a sampling distribution of the sample mean. And the mean what we're calculating here is the mean of the sample means. And the standard deviation that we would be calculating is the standard deviation of all these sample means. Now, one of the things you can notice is that if you take 600 rolls of the die, these means will all kind of hover around the mean of the population. Because if you take 600 rolls, you're going to get approximately an equal number of ones and twos and threes and fours and fives and sixes. And so that when you average them, you're going to get something close to the average, especially if you have 600 rolls. So all of these means that we're plotting in the graph below will be very close to the mean of the distribution right in here. Right in here. And so the mean of the sample means will be very close to the mean of the population. And the mean of the population we just call mu. Now the standard deviation gives us the spread in the data. Now the means are not going to be as widely dispersed, as widely spread out as the actual rolls, 1, 2, 3, 4, 5, 6. Most of our means will be kind of hovered toward the middle. So this, as we'll see later, the standard deviation of the sample means is equal to the standard deviation of the population, it turns out, divided by the square root of the sample size. And so the only thing that's really new in our normal calculations this week is that last number where we do lower bound, upper bound, mean, standard deviation. The standard deviation is not the population standard deviation, but it's the standard deviation of the sampling distribution. And that's this number here. And then to distinguish this statistic from the standard deviation, we're going to call this the standard error. And it's the standard error in this case of the sample mean. The theoretical probability distribution of rolling a die. I didn't draw the graph here, but if I did draw the graph, and the probability was 1/6 here, and we had 1, 2, 3, 4, 5. Well, we would expect about 100, and so 1 would be up a little higher than that. 2 would be up a little higher than that. 3 would be right there, and 6 would be right there, and then 4 and 5 would be a little bit lower. So that's what all these rolls would look like. Not quite, it doesn't quite match the theoretical probability graph, but it's close. Single sample. And then this is one sample, we take the mean, and we do it over and over and over again, roll the die 600 times, and a new graph emerges. And the beauty of this is that under certain circumstances, this graph is approximately normal. And that enables us to do all of our normal calculations. All right, so that's kind of an overview of the difference between the 3 different distributions that we had. And then your notes just kind of formalize that. All right, so we've talked about the sampling distribution. It's a probability distribution for all the values of the statistic. Okay, and the statistic in this section is the sample mean. So the sampling distribution of a sample mean is the probability distribution for all possible values of the sample mean, computed from a sample size of n. So what's consistent in what we've done on that other sheet is that in our example where we were rolling a die 600 times. So the sampling distribution when we roll the die 600 times is going to be different than the sampling distribution of rolling, say, 60 times or 1,000 times. They're all based on the same n. All right, here is the main result. And I've given these to you, formulas, give them to you right here. And then I also mentioned that we call this standard deviation the standard error of the mean and not the standard deviation, so we don't get the two confused. All right, so let's take a look at a few examples using these results. And so it says determine the mean of the sampling distribution and the standard deviation of, or the standard error of the mean is what we call this one, from the given parameters of the population and the sample size. So if we look at, say, number 10, the mean of the sampling distribution is the mean of the population. And the mean of the population is given to us in the problem to be 64. So that's it. The two are the same. And the standard deviation of the sampling distribution that we call the standard error of the mean, there's a formula. And the formula is that we take the population standard deviation and divide by the square root of the sample size. So they give us, in this case, the population standard deviation to be 18, and then we have to take and divide that by the square root of the sample size, which they also give us to be the square root of 36. And this one we can do in our head. Square root of 36 is 6, so 18 over 6 is 3. So they're looking for these two numbers. And when you do a normal calculation using Normalcdf or inverse norm, you always have to begin the problem by identifying these two numbers. The mean is the mean, but the standard deviation, there's a slight change in the formula. All right. Go ahead and do number 12. Put your answers in the chat. You can do this. Mean equals and standard error equals number 12. This one's going to be slightly different because you're going to have to do some rounding. I mean, you're not going to have the square root of 36, a nice number, like 6. Okay, good. The mean of the sampling distribution is the mean of the population, and the mean of the population was given. And then standard deviation is 6 divided by the square root of 15. And good. 1.5492, or some other rounding version of that. Okay, looks like you've got that one. Okay, let's move on to the next one. Now we're gonna say something about the sampling distribution. It's not always that the sampling distribution is normal. There has to be certain conditions for the sampling distribution to be normal. And for most of our problems, we're gonna, just give you problems for which these conditions hold. But at some point, you do have to check that these conditions are hold in order to have a normal sampling distribution. So first thing we know, if in our first example with the die, the population distribution was not normal. It was uniform. What this one is saying is that if a random variable is normal, and you're drawing your sample from a normal distribution, then the sampling distribution will automatically be normal. This one looks to be normal, looks to be bell-shaped. All right, so this one says, answer the following questions for the sampling. So they're telling you that this is a sampling distribution of a mean. So this is the sampling distribution. It's not the population distribution. So there's no need to do any calculations here, but you do have to interpret the graph. So they told you that this one here was the sampling distribution. So the mean of the sampling distribution is the mean right in the middle. So there it is, 12. And then the standard deviation is equal to this. And it looks like you're jumping by 0.05 as you go from 12 to 12.05. All right, so some of these, like this one, it's just a matter of reading the graph. I think we've done that over here, 12. And then the value of the standard error, again, is 0.05. And it says if the sample size is 9, what is likely true about the shape of the population? All right, since the sampling distribution is normal, and we use this idea up here, with such a low, it doesn't really matter. This doesn't put any conditions on the sample size. So up here, I'll just write that n can be any size. And I now realize that this is out of order. So we'll come back to number 14. And I guess you'll see why in a second. All right, the big theorem that we have in this, that makes our sampling distribution normal is this result here. It's called the central limit theorem. And it says regardless of the shape of the underlying population can have a normal distribution. It can have a uniform distribution like our dice example. It can be bimodal, it can be skewed left, it can be skewed right, it can take any shape. But if we have a large enough sample size, then the sampling distribution will be approximately normal. So what they're saying is that if the population distribution looks like this, uniform looks like this, bell-shaped looks like this, skewed one way, skewed the other way, it really doesn't matter what the population distribution looks like. If n is large enough, and our benchmark is going to be if n is greater than or equal to 30, then the sampling distribution of the sample mean, which is our focus for today, will be normal. We saw in our first example that the population distribution looked like this. Our n was larger than 30. It was 600 because we were rolling the dice 600 times. Even though that the population distribution looks like this, if we rolled the die 600 times over and over and over again and calculated the mean, and then plotted all those means, those sample means, we would get a sample mean distribution that is approximately normal. So all of these will look like this, regardless of what they look like, if n is large enough. And by large enough, we mean 30 or more. So there's two conditions under which the sampling distribution will be approximately normal. The first thing is if the underlying probability distribution is normal. Okay. So that's this one here. If the population distribution looks like this, then the sampling distribution is going to look normal, just like this, or a little bit different, but it's going to look normal. It doesn't matter what the sample size is. The second scenario is that if n is large enough, the original population distribution can look like anything, yet the sampling distribution will be approximately normal. So everything is leading to a normal curve if you begin with a normal distribution, population distribution, or you have in your sample a large enough sample size. Not only that, we know that the mean of the sampling distribution will be the mean of the population, and the standard deviation of the sampling distribution that we call the standard error of the mean will be given by this formula. Okay. Now, going back to this question. If the sample size is 9, that's less than 30. So if we did end up with the normal sampling distribution, what probably was the case is that the original population had a normal distribution to it. So the shape of the population is approximately normal. Because our sample size was not large enough to yield a normal sampling distribution in all cases, if we do get a normal sampling distribution, normal looking sampling distribution, then probably the original population distribution had to be normal. And if the sample size is 9, what is the standard deviation of the population? What is, well, we have this formula. Since the original population was probably normal, then we do know this number is right here to be 0.05. So they're asking a question about what is the population distribution, and they give us the sample size of 9. So you can deduce what the population standard deviation. One of the difficult parts about this section is that, you know, you have to link word phrases to symbols. And so I talk about the standard deviation of the sampling distribution. And when I say that, you need to think this variable. Or when I say the sampling or the standard error of the sample mean, you have to think about this answer or this variable here. Whereas that sigma there is the population standard deviation. All right, so the rest of this is, we know that the square root of 9 is 3. So if we multiply both sides by 3, you get 0.15 there. So it says, what is the standard deviation of the population from which the sample was drawn? Well, it was probably 15, 0.15. So that when we divide 0.15 by 3, we get this 0.05 that we know to be the standard error in this case of the sample mean. Okay, now it's time, now that we kind of have defined that and what the standard error and the mean are of a distribution, there are lots of problems that we can do. So let's take a look. This first one doesn't really have a context, but I do want to point out some of the notational things that will be different. Now, when you're calculating a probability in a sampling distribution, instead of just saying the probability that X, some generic value of the random variable, is less than 67.3, we're now going to ask a probability in terms of a mean, a sample mean. So what's the probability that the sample mean is less than 67.3? Now, the calculations we do here are identical to what we would do in the chapter 7 problems. The only difference is that the standard deviation, that last number we enter into normal CDF and inverse norm, that last number, we have to use not the standard deviation, but the standard error. So let's take a look at how one of these would work. And I'll do a couple, and then maybe I'll ask you to do one. All right, first of all, we have n is equal to 20. And n is equal to 20, that's less than 30. So we can't be guaranteed that we have a normal sampling distribution. Okay, so part A, what must be true regarding the distribution of the population in order to use a normal model to compute probabilities involving the sample mean? Okay, if we have a small, less than 30 sample size, then in order to use our normal calculations, we must have that the original population is approximately normal. So what must we assume? The population distribution is approximately normal. If a random variable is normally distributed, then the sampling distribution is normally distributed. And if the sampling distribution is normally distributed, then we can use all of our normal calculations. All right, then they say, assume that this condition is true. Okay, so now we know we have a normal sampling distribution. It says describe the sampling distribution of X. All right, so you want to say something like this, X bar. X bar is approximately normal with the mean of the X bars equal to the mean of the population, which in this case is 64, and the standard deviation of the sampling distribution, we call this the standard error of the sample mean, is given by the standard deviation of the population divided by the square root of the sample size. We do know that 17 is the standard deviation. We do know that the sample size is 20. So if you wanted to get a decimal approximation to that standard error, let's punch it into the calculator. And it's about 3, I'm just going to call it 3.8. All right, now let's go into B, and I want to show you how the normal calculation of probability in a sampling distribution is done. Okay, so part B says, assuming the requirements described in part A are satisfied, determine the probability that X bar now, change a variable from what we've done earlier, is less than 67.3. As before, I'm going to ask you until you can visualize this sampling distribution and the mean and the standard deviation in your head, that you draw the graph. So we know that the sample, anytime they ask a probability about X bar, we know something about the sampling distribution of X bar. It has a mean of 64 and a standard deviation of about 3.8. And with those two numbers, we're going to draw our graph. We know that the sampling distribution is approximately normal, where the mean of the sampling distribution is equal to the mean of the population, and in this case that is 64. And the standard deviation is 3.8. And again, this is the standard deviation of the sample mean that we call the standard error. All right, so I'm going to label this scale using the 3.8 as my scale marking. And then this would be 67.8 and then 71.6 and 75.4. Going back the other way, this is 64, subtracting would be 61.2. And then 57.4, and then 53.6. Do this however you've done it in the past. Then we're going to shade the region that corresponds to this event or this probability that we're going to calculate. So this whole distribution is the distribution of X bar. It's called the sampling distribution. And we want to know the probability that a randomly selected mean is less than 67.3. So we're going to identify 67.3 on our horizontal scale. It's about right there. Just less than 67.8. And that symbol means less than. So we're going to shade all of the region that corresponds to these X values that are shaded there. So here is the shaded region. All right, now that I see the picture, I know that a normal probability can be calculated on my calculator using Normalcdf. So again, I need to specify the 4 numbers that make this function work. And that would be the lower bound, in this case, negative infinity. So just as we've always been doing, we'll use negative 10,000. The upper bound is 67.3. And then we have the mean and standard deviation. The mean is 64. And the standard deviation is now the standard deviation of this picture, standard deviation of sample mean, call that the standard error. So we're going to be using 3.8. So a big part of your problems today will require that you change this last number relative to what you've done in the past. But once you get those numbers identified, then you can just go ahead and enter them into the calculator's Normalcdf function to get your probability. Now, we know from looking at the shaded region that it's more than half. In fact, it almost goes up to here. And if it had gone up to there, then we'd have 50% and 34%, that's 84%. And it's a little bit less than 84%. And the calculator tells us it's 0.08074. Okay. Why don't you go ahead and do part C? I'll give you a minute. Oh, okay, did I get that wrong? Emerson corrected me here. It's not going to change our answer here, but I have this scale wrong. This should be 60.2. And that's going to change these other ones here. Go ahead and do part C. Probability that X bar is greater than or equal to 65. Okay, so just note that this is a probability. So whatever you put here, it has to be a positive number. Any probability, including this one, has to be a number between 0 and 1. Okay, it looks like 0.3761. That makes sense to me because we're going to go from here on over. So I know that it's less than half of the area. And so that seems like a reasonable number. Normalcdf, now we're going from 65.2 up to positive infinity. And so you're going to have a collection of greater than probabilities, less than probabilities, and even between this probabilities. So if you punch all this in, 0.3761. All right, let's do one last problem in this section, and this is the true a true application problem. As before, what I'll do is I'll do all of these problems. So if you want some more problems to refer to in the lecture notes, you can go online after class and see the answers to the rest of these. But because of what we need to do in class, I'm going to just do maybe 1 or 2 problems here. All right, how about number 30? ATM withdrawals. According to Crown ATM Network, the mean ATM withdrawal is 67. Okay, mean equals 67. They're not saying anything about a sampling distribution. They're talking about, of all the ATM withdrawals, the average is about $67. Assume that the standard deviation for the withdrawals is 35. Now they said standard deviation and they didn't say standard error. So the way we interpret that is with sigma and not sigma sub X bar. All right, let's read on. So we kind of know what the population looks like. Didn't say anything in here that the original population was approximately normal. Indeed, we probably would expect it not to be normal. Oh, and that's the first question that they ask. Do you think the variable ATM withdrawal is normally distributed? If not, what shape would you expect to have? Right, so it's probably not normal just because, I don't know, when I go to the ATM, I always take out the maximum that I can, like $200. And if there are other people like me, it seems to me that they're going to allow the maximum, whether it be 200 or 300. The other thing is people tend to take out multiples of 5. You know, no one asked for $23. I suppose they could, but usually we ask for multiples of 5. So there's some popular answers like 20 and 40 and 60 like that, and you're going to see very few in between. So I'm expecting this not to be normal. I would say it might be skewed to the left because, yeah, I guess it really depends on the age cohort. But so I would say that this is probably not normal. All right, now our sampling distribution, if it is not normal, could be possibly normal as long as we have a large enough sample size. Our benchmark is 30 or larger. So in part B, it says, if a random sample of 50 ATM withdrawals is obtained, so what they're telling us here is that our sample size is 50, and 50 is larger than 30. So therefore, if we looked at a bunch of different sample means where the sample size was 50, all of those sample means would have a sampling distribution that is approximately normal. It says, describe the sampling distribution of the mean withdrawal amount. So we would say that X bar is approximately normal with the mean of the sampling distribution equal to the mean of the population that we identified up at the top to be 67, and the standard error given by our standard error formula is 35 divided by the square root of the sample size. And as an estimate, 35 divided by the square root of 50, which is approximately 4.9, we'll call it 4.95. And then C is to determine the probability of obtaining a sample mean amount between 70 and 75. So what's the probability that, again, our probabilities will be written in terms of X bar in this section as opposed to just a single data value X, n is equal to 50, between 70 and 75. So there's the application. If we know the mean of the sample means, this is part C, is equal to 67, and the standard error of the mean is 4.95. And we draw our normal curve with 67 in the middle. And I'm not going to take any chances at calculating things incorrectly, but let me just take 67 and then add the 4.95 once, twice, 3 times. And then do the same thing, but subtract to get the numbers on the other side. 62.05, 57.1, and 52.15. And then in part C, they want us to calculate the probability that X bar is between 70 and 75. All right, so 70 is in here somewhere. Well, let's just call it right there. And 75 is over here somewhere. And so the region that we're interested in is this little slice here. We can see that slice is relatively small with respect to the whole area under the curve, certainly less than 1/2. But drawing the graph enables us to set up the calculator function that we need. Normalcdf. And then lower bound 70, upper bound 75, mean 67, and standard deviation 4.95. And then the rest of it is just to punch it into your calculator and evaluate, and then interpret if you're asked to do so. 2192. So you can see the calculations are similar. I have not yet done a problem that uses inverse norm, but you'll see those as well. Okay, now the next section, 8.2, is very, very similar. In fact, it parallels what we just did. It's just that we have a different sampling distribution here. This is going to be the sampling distribution of the sample proportion. So we have one of our most popular statistics is the mean. So we look at the sample mean distribution. Our other most important statistic is the sample proportion. So we want to look at the sampling distribution for a sample proportion. Now this one is different, but I will go on to say that we still have the 3 different distributions: a population distribution. And what's interesting here is that for a proportion, we're really working with qualitative data, not numbers, not numerical data, qualitative data. So an example here could be flipping a coin. And if this is the probability, the outcomes down here are not numbers like they were with the dice example. I mean, all we have are heads and tails. And let's say we're going to flip a coin 100 times. So if the probability would be 1/2, but if we did the frequency would be 50. And we would expect 50 heads, and we would expect 50 tails. If we flip the coin 100 times, this is what the distribution would look like. Now p hat is equal to the sample proportion. P is the population proportion. And in this case, for the probability distribution, the population proportion, and this would be, you know, the proportion of heads that we would expect in the population, if we flip the coin 100 times, would be 50 and 50. The population proportion would be 1/2. Half the time you get a head, half the time you get a tail. The sample proportion is defined to be x over n. And so if we now look at a single sample, it could be the case that when we flip the coin 100 times, it could be the case that this is 50, that the number of heads we get might be, say, 52, and the number of tails. But this is just one single sample. So one possible sample we could get would be one that looks like this. Let's say that our success was flipping a head. So in our sample, the probability of flipping a head would be 52 heads out of the 100 tosses. And for our sample proportion, we would get 0.52, which is very close to the 0.5 in the population. But this is based on a single sample. All right, so here's the big jump. The third graph we're going to draw is the sampling distribution. Now these here are like bar graphs because they deal with qualitative data. The sampling distribution is a different animal, because what we're going to do is we're going to take a random sample of 100 coin tosses and calculate the sample proportion in each case. Notice that all of these sample proportions will be numbers. It might be 0.52 the first time, it might be 0.47 the second time, and the next time after that it might hit 0.50. But just think of all the different sample proportions that you would get if you flipped a coin 100 times and just recorded the percentage of, or the proportion of heads that you get. Most of those outcomes would be very close to 0.50. And if you plotted them, most of those p hats would be close to 0.50. One might be there, you know, if 0.52 is over here, we just got 0.52. But what you would see is all of these sample proportions start to form a graph, a histogram. And as you might expect, under certain conditions, that this sampling distribution of the sample proportions is also going to look bell-shaped. So in this section, we look at the sampling distribution of p hat. And as before, we're going to say that p hat is approximately normal. And generally, it's a claim about the sample size. So if, and the criteria that we use is n times p times 1 minus p has to be greater than 10. This is our sample size criteria. If n times p times 1 minus p, sometimes I'll just say n times p times q, is less than 10, then we must use binomial probabilities or binomial distributions to calculate probabilities. Otherwise, we can use the normal calculations. And it turns out that if this criteria is met and our sample size is in fact large enough, then the mean, notice my variable name, it's not the mean of the means, it's the mean of the p hats, is going to be equal to the population proportion, which in our case here is 0.50. And then here's a new formula. The standard deviation of the sample proportion, we're going to call that the standard error of the sample proportion, is given by this formula, square root of p times q, or 1 minus p, divided by n. So our problems will parallel what we did in the other section, but if you're asked a probability that p hat is, you know, less than, say, 0.49, then if this criteria is met here, go ahead and check it. N times p times 1 minus p is equal to, in our case, the n is 50. No, the n is 100. We're rolling the die 100 times. The probability of a success, getting ahead on each trial, is 1/2. And then 1 minus that is also 1/2. And 1/2 times 1/2 is 1/4 times 100. And you get 25. And 25 is larger than 10. So therefore, the sampling distribution is approximately normal. But you really should check, you know, this condition. If it doesn't hold, then you're forced to use binomial probabilities. All right, let's take a look at a couple of problems in the short time that we have left. All right, here's a very brief, very easy, but very important formula. Formula for calculating the sample proportion, p hat. And this talks about what the sampling distribution is, the condition we need, what the mean and standard deviation are. So we've defined those. And now let's look at a couple of problems. The first one is, it says describe the sampling distribution of p hat. Assume that the size of the population is 25,000. In number 10, we need to check n times p times q. Is it larger than 10? We need to check that. So for number 10, we have n is 1010. The p-value is 0.84. And so the q-value is always 1 minus p. 1 minus 0.84, which is 0.16. And I think this sample size is going to be large enough, but we'll just multiply it out. And notice that this is about 135.744. The important thing is that it's larger than 10. And if n times p times q is larger than 10, then based on what we said before, we can conclude that p hat is approximately normal with the mean of the p hats equal to the population proportion, which in number 10 was given to us to be 0.84. We also know that the standard error of the sample mean is given to us to be this formula here. Mean of the p hats equal to. So we're going to take the square root of p times q over n. In this case, the square root of 0.84 times 0.16 divided by 1010. And that's going to be a very tiny number. Remember, these are proportions. So square root of 0.84 times 0.16 divided by 1010. And that number is approximately 0.0115. All right, so the answer up here is all of this and basically this work right here. Here's your answer. So it says, describe the sampling distribution. We check to make sure that the sample size is large enough by confirming this formula. We see that it's n times p times q is larger than 10. And then if we know the sampling distribution is approximately normal, we can calculate the mean and the standard deviation of the sampling size, looking at these two formulas. And then we conclude that p hat is approximately normal with mean equal to 0.84 and standard deviation equal to 0.0115. And then as soon as we know that, we can do all kinds of probability calculations. But you can see what the probability calculations will look like. At least the symbols would be looking like this.